In problem number 16, we have this function here, x cubed plus x minus 1, and we want to find all the numbers that satisfy the conclusion of the mean value theorem on 0 to 2. So it's really important that it's on that specific interval. So remember that the mean value theorem states that if you have an interval, the slope between those 2 points on this function has to be equal to the derivative somewhere in between, as long as your function is continuous, and we have a polynomial which is continuous. So what we're going to do is take the derivative and set it equal to the slope that we get by using these 2 points. So the derivative here is going to be 3x squared plus 1 by just using our power rule. So that derivative has to be equal to the slope that we would get by using 0 and 2 as endpoints of a line from this function. So what we're going to do is set this equal to f of 2 minus f of 0 over 2 minus 0. So that's y2 minus y1 over x2 minus x1. So that's the slope. So let's plug those in and see what we get. So 3x squared plus 1 then is equal to, if we plug in 2, we would get 8 plus 2 minus 1, so we get 9. If we plug in 0, we get negative 1. And that's all over 2. So you can see there we end up getting 5. 10 over 2. So we get that 3x squared plus 1 has to equal 5, and now we can solve for x. So we could subtract 1 over and divide by 3, so we get that x squared is equal to 4/3. Therefore, x is equal to plus or minus the square root of 4/3, which I'll just leave like that for now. So these are the x values that if we plug those, or the slope at those points is equal to this slope that we got here. So the derivative, remember, tells the slope at a point. So these 2 points have slope equal to that. But the mean value theorem only guarantees points that are within the interval. And notice that we have plus square root of 4 over 3 and minus square root of 4 over 3. But our interval was 0 to 2. So the only value of c that satisfies the mean value theorem is positive square root of 4 over 3, not negative. So then part B to this says, use information about the derivative to show that it only has one real root. Okay, so what we're going to do then is look at our derivative here and notice that our derivative is 3x squared plus 1. So what that tells us is no matter what we plug in for x, this derivative is always going to be positive. So therefore we can say f of x is increasing negative infinity to infinity. It is always increasing. So if our derivative is always positive, that means our function is always increasing. And if our function is always increasing, as long as we touch 0 one time, remember a function having a root means that it crosses the x-axis, it could never touch it again, because in order to touch the x-axis twice, if you have any function, if it touches it once like this, if you were to touch the x-axis again, it would have to come back down. But we can't decrease. This function never decreases, so we couldn't do that. So we can't have that situation going. So to prove that it only has one real root, the only other thing we need to show is that, well, does it touch it at least once? Because it's possible to have a function that always increases that doesn't touch 0 at all, like something like that, like an e to the x type graph. So we know it's always increasing. We just need to make sure it touches once. But if you notice, this is a polynomial and it's odd degree. So that automatically tells you that at the positive end it goes to infinity, at the negative end it goes to negative infinity. So it definitely has to go through the x-axis once. So by using the fact that this is a polynomial of odd degree and therefore has to go negative infinity to positive infinity, and our derivative is always positive, that shows us that this function could only cross the x-axis one time, meaning that it only has one real root.
The Teaching Center, UF's Learning Resource Center.